Mikrofon açık kaldı galiba. Şimdi fark ettim. Okay. So we were at example 2, and again here as example 1, we will try to find an absolute x1 values of function xy plus x square, which is two variable function, as you can see, and we try to find that absolute x1 values on the restricted region here, which is the triangular region D, given by those inequalities. So if we just sketch the region D, or you can call it region T, triangular region, it will be, so x values are in between -1 and 1, and on this area between those two lines, let's say, y is in between the lines x minus 1 and minus x plus 1, or 1 minus x. So this is the line, that one is the line minus x plus 1, and the other one is x minus 1. So that will be the region, this will be the region D. This is the region. And first, we will start by computing the first partial derivatives to find out the critical and singular points. So we will find first f1 xy and f2 xy. f1 xy is y plus 2x, and f2 xy is x plus 0, so which will be x. And then we will try to see where the gradient is 0. So it is only at origin, and where it is not defined, it is defined for any xy on xy plane, so it has no singular points. And that means this is the only point that we will compare by the others, where f is 0. f00 is 0. So this is the critical point. And now we will try to parameterize those line segments. So the boundary of the domain in the triangular with vertices. So those will be the vertices 1, 0, minus 1, minus 2, and minus 1, 2. So those are the vertices of the triangle. So the size of the triangle, or the sides of the triangle, can be parameterized by the line segments like that. X equals minus 1, so this one, that line segment. X equals, okay, let's see. So x equals minus 1 between y equals, y in between minus 2 and 2. So this will be the first parameterization. And second one will be y equals minus x plus 1, this line, minus x plus 1, in between x values, minus 1 and 1. And the last one is y equals x minus 1. Again, this is defined for x values in between minus 1 and 1. So those are the line segments of the triangle that we have as a restricted domain. So in each side of the triangle of our function f can be reduced to a function in a single variable. So how it can be? So you can define the first function here, x equals -1 and y is in between -2 and 2, as if you try to write the function as x equals -1, so the function is xy plus x squared, so that means you can define it as minus y plus 1 on that line segment. So this can be defined as g1y equals minus y plus 1 in between y values minus, where the y values are in between -2 and 2. And now we will try to write down the second the function on the second line segment, where y equals minus x plus 1. So if you just write again on the function instead of y minus x plus 1 here, and you can see here, and you can see the function defined as one variable function as x, so it will be equal to x for the x values in between -1 and 1, so for that line segment. And for the last one, y equals x minus 1, the function will be defined as you will just write instead of y x minus 1, and then you will see that it is defined as 2x squared minus x. So this is how f is defined on the last line segment here. Again, the x values are in between -1 and 1. So here, as you can see, now it becomes a extreme value you can say problem on one variable functions. So we can compute the extreme values of above functions on the specific domains, and those are the domains of the functions. So this is for the first one, this is the closed interval -2, 2. For the second one, it is closed interval -1, 1, and also for the third one, it is the same. So those are the domains. So on those, between those domains, let's say, we will try to see what are the extreme values of those g1, g2, and g3, all these functions. And if you just solve those, try to find that extreme values, and we can see the maximum and the minimum values on the boundary are 3 and -1 respectively. And we had another candidate of extreme value which is on critical point, so which is 0. So after that you will compare all these values, 0, -1 and 3. So then conclude that -1 is the smallest value here and 3 is the biggest one. So 3 is the absolute maximum and -1 will be the absolute minimum value of the function on that triangular region D that we shaded above. So as you can see now, this is one of the I guess those are the vertices, one of the vertices of the region, restricted domain, -1, -2, and -1, 2. Let's say that. Okay. So for our function, which is xy plus x square, the function gets its minimum value on that vertex here, and the maximum value on the other vertex, which is the point with coordinates -1 and 2. So those will be the extra values of fxy on that restricted domain. So this is the last example for extra values of functions defined on restricted domains. And now we will continue by Lagrange multipliers, which will help us to find again extra values for restrictions, one restriction or more than one. We will see that. And here we will, let's say, we will consider constrained extra value problems. For example, the maximizing, minimizing problems where the variables are related by an equation called the constraint. So those will be constraint functions. Functions and constraints in concern may involve 2 or 3 variables, and we may have different types of constraint extra value problems. For example, here, maximize or minimize any 2 variable function subject to gxy, the constraint function here will be gxy equals 0, or maximizing, minimizing a 3 variable function subject to the constraint inequality here, which is 3xyz smaller or equal to 0, or can be greater or equal to 0. So in the second example of extra value problems, the constraint, as you can see, is given by g, the g function, constraint function, smaller or equal to 0. So in that kind of constraint functions, we can separate the region as g is smaller than 0 and g is equal to 0, and then we will find the extra values separately for each of these 2 regions. For the case where g is smaller than 0, it is, for that case, it will be enough to find the critical and singular points of the function f, satisfying that inequality that we have seen on the theorem on the previous chapter, chapter 1, and then after that our main focus is the set of the points satisfying g equals 0, which is clarified by the following theorem. So those are will be the steps of where the constraint function is like g, x, y, z smaller or equal to or greater or equal to 0. So if we have f and g as 2 variable functions with continuous first partial derivatives around the point x0, y0, satisfying g x0, y0 equals 0. So this will be the constraint function. Suppose also that f x0, y0 is a local extremum of f on the set of points satisfying gxy equals 0. And also, by supposing p0 is not end point of the curve given by the constraint function gxy equals 0, and the gradient of g at p0 is non-zero, then there exists lambda 0 such that x0, y0, lambda 0 is a critical point of that function, which we will call as Lagrangian function, Lagrange function. So it will be Lxy lambda equals fxy plus lambda times gxy. So this is our function, and this is the constraint function gxy. And note that if the function f and g involve three variables, here we have f and g as two variable functions, but involve three variable functions, then the theorem that we have seen here still holds. And if we just try to see what it means, the theorem, the critical points of the Lagrangian are points xy lambda satisfying, since it is the critical point, since we will find the critical point of Lagrangian function, those have to satisfy the first partial derivatives. All the first partial derivatives is 0, and if you focus the last equation we have here, 3xy lambda equals gxy equals 0, actually that one is the constraint function. So the third equation guarantees that our point obeys the constraint. This one. That one gxy equals 0. The first and second conditions above can be combined, those two, first one and the second one here, can be combined, and by using the definition of gradient vector, we can write those two equations as gradient of f plus lambda times gradient of g equals 0. So we will look for the points on the constraint function where gxy equals 0, at which the gradients of f and g, the both here, differ by a constant multiple, which is minus pi in the above notation, because we can write the gradient of f equals minus pi times the gradient of g xy from that equation. So that is why it is minus p in the notation that we write here. Indeed, there is the idea for the proof of the above theorem. If we let u as the projection vector of gradient vector of f at AB on the gradient vector g at AB, so we can define it by that notation for some point AB, then f has, that means f has positive directional derivative along the gradient of FAB minus u. And if we say f has a negative directional derivative along gradient of AB minus u, which is the projection of gradient of f at AB on gradient of g at AB, then it will be the direction, if it is negative, it is direction derivative along minus gradient of f minus u, to have the directional derivative to have the local extreme value. So it cannot have a local extreme value at that point A, B. That is the brief, let's say, proof of the theorem. And if we try to see how will be the application, so we will try to find the absolute maximum value of x times y on ellipse x squared plus 2y squared equals 1. So we need to maximize the function because we try to find the absolute maximum value, which subject to gxy x squared plus y 2y squared minus 1 equals 0. So this will be the constraint function because we try to see the maximum, absolute maximum on that ellipse. This is gxy equals 0 will be x squared plus 2y squared minus 1 is a constraint function. So now we can parameterize the ellipse and then reduce as we did. So you can solve this example as we did as on previous chapter. Then try by parameterizing, then after that defining it is in a single variable, and then solve that maximizing problem. But here we will use, instead of this method, we will use Lagrange multipliers. Okay, and also let me say that here the lambda, those that can be two more than one constraint. So that lambda, which is the multiple here, constant multiple here, will be called Lagrange multipliers. So those are the Lagrange multipliers. So we will define the Lagrange function here as fxy plus lambda times gxy, so which will be xy, which is fxy, x times y plus lambda times gxy. So this will be the Lagrange function. And we know that the critical point will be defined by taking the partial derivatives of Lagrangian function. So if you try to find L1 xy lambda, then it will be the first partial derivative of Lagrangian function with respect to x, so which will be y plus 2 times lambda x. So here you have, if you just try to find the partial derivative, it will be 2x times lambda. So you can write this 2 lambda x equals 0. Also you can simply find the other partial derivatives here. So the last one has to be the gxy. So from first two equations, we will try to solve those L1 and L2 equals 0 together. And if we solve that, that gives y equals 0 or lambda equals plus or lambda equals minus 1 over 2 square root of 2. But if you try to write that y equals 0 on the, let's say, on the first or second one, let me see. Okay, any of them. So if you try to write y equals 0 on first or second equation, it doesn't matter, you can see that x equals 0. That implies x equals 0, but then that will be a contradiction if you just let x equals 0 and y equals 0 in the last equation here, which is gxy actually. So you will get minus 1 equals 0, so which is a contradiction. So that is why the only option that maybe has to be here, the lambda is equal to plus or minus 1 over 2 square root of 2. So in any case, plus or minus case, we find x as telefonun sesleri çıkardı arkadaşlar. So the lambda, for any lambda here, let's say,
Hocam sesinizi duyamıyoruz biz. Arda hocam, sesinizi duyamıyoruz. Mikrofonunuz kapandı.
şimdi geliyor mu sesi?
Geliyor.
Tamam. Ben sanırım başkasının mikrofonu kapatayım derken kendi mikrofonumu kapattım. Tamam, baştan anlatayım şu kısmı o zaman. Okay. So when y equals 0, then it implies from the first or second equation x equals 0, but it will have a contradiction with the third equation here, because it will be 0 plus 2 times 0 minus 1 equals 0, so which will be minus 1 equals 0. So that is why y cannot be 0, so that the first case cannot happen. So only option that lambda equals plus or minus 1 over 2 square root of 2. And by that assumption, or by that conclusion, let's say this one, from the first and second equation we can write x as plus minus square root of 2 times y. And by letting this on the third equation, and also by letting lambda as one of these variables, we have 4 points, which will be plus, 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 minus, minus, plus, or plus, plus. Sorry, minus, minus, 1 over square root of 2, 1 over square root of 2. So those will be the 4 points. And from the theorem, we know that the maximum will be attained one of those critical points. So that is why we have to compute the function for all these points. Then after that we have to compare all these points, the value of the function on those points, let's say. And if we do that, we can see at point 1 over square root of 2, 1 over 2, and at minus 1 over square root of 2, minus 1 over 2, the function gets its maximum, absolute maximum value, which is 1 over 2 square root of 2. Okay, so as you can see, it is much easier to see the extreme values by using the Lagrange multipliers. And here let's give another example, which now have 3 variables, x, y plus z, and we will try to find the minimum value of the function on unit sphere, so which is a sphere with the equation x squared plus y squared plus z squared equals 1. This is the unit sphere. So since the unit sphere is closed and also bounded, a bounded region, the function f on that unit sphere must have an absolute minimum from the theorem that we have seen on previous chapter. So our problem is to minimize now. This is the minimizing problem. X, y plus z subject to constraint function gxy, which is x squared plus y squared plus z squared minus 1 equals 0. So you have to write the constraint function as g equals 0. Okay, so since this is your restricted domain, this is your then the constraint function has to be x squared plus y squared plus z squared minus 1 equals 0. So now we can write the Lagrange function, which will be defined as fxy plus lambda times gxy. So this will be xy plus z, which is fxy plus lambda times gxy. And now try to find the critical points. We will find first partial derivatives of Lagrange function with respect to x, with respect to y, with respect to z, and then with respect to lambda, which will give the constraint function. And after that we have to solve those equations, those 4 equations. From the first and second equations we get x, y equals 0 or lambda equals plus or minus 1 over 2. And if we let the second case, where lambda equals plus or minus 1 over 2, we have z as plus or minus 1. And again, we have, for that as let's say, for these values of z, x equals y, y equals 0, all x and y equals 0. So after solving all these equations together, then we will have 2 points which are 0, 0, 1 and 0, 0, minus 1. And if we just compute the value of the function on 0, 0, 1 and 0, 0, minus 1, we can see minus 1 is the smallest value in between those two values. So that has to be the absolute minimum value of fxyz on that unit sphere. So this is an example for 3 variable functions. And also, as I said on the beginning of that chapter, we also can consider problems with more than one constraint. All the examples that we have seen had just only one constraint function, but it can be more than one. For example, if we assume a problem for example maximizing or minimizing fxyz subject to two constraints, which are gxyz equals 0 and hxyz equals 0. Has a solution at point P0, then the intersection of those constraints will be a curve with the tangent vector, which will be found by the cross product of gradient of g at P0 and the cross product of gradient of the other constraint h at P0. Then the gradient of f at P0 must be perpendicular to that tangent vector, because otherwise f has non-zero directional derivative along plus and minus tangent vector, so it cannot have a local extreme value. But that tangent vector t is already perpendicular to gradient of g at P0 and also gradient of h at P0, because from the cross product we know that those two vectors both perpendicular to tangent vector. Then the gradient of f at P0 must be in the plane determined by those two gradient vectors of g and h at P0. Then we can say there exists lambda 0 and mu 0, or you can call lambda 1, lambda 2, such that x0, y0, z0, lambda 0, and mu 0 is a critical point of the above Lagrange function. As you can see here, you have two constraint functions, which are g and h, and you have two Lagrange multiplier, which are lambda and mu. So this will be the Lagrange function of f, for minimizing, let's say f, or maximizing f, but with those two constraints. And if we try to maximize x, y times z, for example, 3 variable function subject to two constraints like here, x plus y plus z equals 0 and x squared plus y squared plus z squared equals 0. And let's see what will be the maximum, absolute maximum value of f for those two constraints. So first, again, we have to write the Lagrange function, which will be fxyz plus lambda times gxyz. So gxyz here will be x plus y plus z plus minus 0 equals 0. So which will be x plus y plus z plus mu times, and hxyz will be the other constraint function, which will be x squared plus y squared plus z squared minus 6 equals 0. So which will be x squared plus y squared plus z squared equals 6. So after writing the Lagrange function, we need to find the critical points. So that's why we have to find first partial derivatives of Lagrange function with respect to x, y, z, lambda, and the last one with respect to mu. Here, the last two equations, L4 and L5, here will be denote the constraint functions, let's say gxy and hxy, z, respectively. So we need to solve all these equations to find the critical points. So by subtracting L2 from the equation L1 here, we can find y minus x times z minus 2 mu equals 0. Similarly, if you subtract, I guess, L2 from L3 and L3 from L1, or vice versa, you will find z minus x times y minus 2 mu equals 0, and also z minus y times x minus mu equals 0. Considering all those possible cases, by concerning also L4 and L5 here, we will find those critical points. So that means we have to find the value of the function f x, y, z at those 6 points, and after that we need to compare all the values, and we can see minus 2 is the absolute minimum value of f x, y, z by those two constraints, and also 2 is the absolute maximum value of f x, y, z for subject to those two constraint functions, G and H. Okay. Tahminimden erken bitti. Şöyle bir sadece konuyu buldum ama bir saniye bekleteceğim sizi. Neyse, yine bitirdim. Yani kataloğu sesini kalıyor. Hiç yapayım dedim ama mouse'u geçiriyorsunuz. Evet, evet. Açılmıyor, dokunuyor o yüzden maalesef başlayamayacağım.